Great. Well, thank you very much for inviting me. I think before I start, I just want to make clear a few things about what I'm not claiming. I'm definitely not claiming to have a complete answer to this question, and I'm not claiming to have a better answer than you're likely to have. I know I'm talking to a room full of people who've been thinking about this very question. And you'll have different perspectives on it. And I'm not claiming that my perspective is better than anyone else's. I just want to talk about my perspective on the question. Um, and also, I'm not at all a machine learning expert, so I may accidentally sort of make remarks about machine learning can't do this, and then if you know more about it, your reaction will be, well, what about so and so or such a paper that came out recently that's doing exactly what you said it can't do. And I'm sure there will be examples like that. Nevertheless, I hope that sort of some approximation of, I mean, what I say will be some approximation to something. So it's a sort of weak thing that I'm aiming for. Basically, I just want to present how it looks to me at the moment from my perspective as a mathematician who's not at all a machine learning expert. But somebody who has played around quite a lot with LLMs, particularly actually ChatGPT. I haven't used as much as I should some of the other ones, although I recently started using Gemini 2.5 because that seemed, well, when I say using, I mean experimenting with, because that seems to be, I find that one a very good one. Okay, so um, let me just start by some of the questions that one might ask while thinking about why they aren't better than they are. By the way, when I say why aren't they better, that doesn't mean they're not already reasonably good. So it just means why are they not better than they actually are. Um, so I think a question that is sort of fundamental that we all think about is what level of thought is going on. And at one end, you have people who say that they're nothing but stochastic parrots, and at the other end, you have people who say they're already thinking in a very genuine way. And once we scale up, then this thinking will become deeper and deeper, and eventually they will be better than we are. And that's the second question. Then is scaling up enough? Um, then we certainly at the moment it's the case that hallucination is a significant technical obstacle when you want LLMs to do mathematics, because if you want to build an argument with lots of steps, and if some of the steps, it just takes one step to be hallucinated, and the whole pack of cards can come falling down. And we see that that happens a lot when LLMs do mathematics. When they run into trouble, instead of saying, I don't know the answer, they just pretend that they do know the answer. And then sometimes it's quite difficult to see where they've gone wrong, and or sort of annoying to check. Um, and looking more sort of optimistically, we can ask whether there are whether even if they're not perfect, is it the case that there'll be certain things that they are really good at that will be quite useful to us? I can actually speak from personal experience in the last few days. Just the fact that ChatGPT can help me program has enabled me to do some mathematical experiments related to my own research that I would just not have had the patience to do um, without. So I just described in detail how I wanted an algorithm to work, and ChatGPT came up with a Python script to do it very quickly. And then we had some back and forth, and I got it to do more things. And so I've been very excited about that over the last 2 or 3 days. So, and that's just one thing that they're already useful for. Maybe a slightly deeper question is, are there any sort of fundamental obstacles, at least for LLMs as they work at the moment? Or maybe I could even ask more, are there tasks that you really have to be a human being to do that LLMs would never be able to do? By the way, I might as well say right now, I don't believe the answer to the last question in a strong sense is no. I think eventually they should be able to do pretty much everything. But I think that's not to say there aren't obstacles to get there. But I'm basically I don't know whether the right word is optimist or pessimist, but I think that AI is going to be able to do serious mathematics. Probably not that long from now. I won't put a timescale on it. We all think about that as well. Let me now quickly move on. So I want to talk about a number of examples, and I want to stress with these that the purpose of these is not just to sort of laugh at LLMs when they get them wrong, because that's an easy thing to do. One can always just set examples and watch them hallucinate and so on and so forth. But really just to think about the way in which they go wrong when they do go wrong. So I want to start with an example from additive combinatorics. So a little warning, this talk will have a bit of mathematical content in it, but I hope it's not going to be that difficult. So let me just quickly discuss. Also, I thought that actually, because I'm coming at this from a mathematical angle, maybe discussing actual mathematics is something where I can be more useful than if I just speculate as an amateur about the machine learning side of things. So if you take a set of integers, we define its sum set to be the set of all sums that you can make out of two elements of the set. So as written there. And we call the doubling constant, we think of a plus a as being the sort of doubling of a, and the doubling constant is the ratio of the size of a plus a to the size of a. And this is a quantity that's of huge interest in additive combinatorics, in particular because there's a theorem called Feynman's theorem that it gives you amazing structural description of a set if it has a small doubling constant. That I'm not going to go into. That would be a completely different talk. But here's a simple example. If you take a to be a set of numbers from 1 to n, then a plus a is a set of numbers from 2 up to 2n. And then the doubling constant is approximately 2, or when n is large. And that turns out to be the best you can do, to take just an interval of integers like that, or equivalently, because it's sort of affine invariant, you can take any arithmetic progression of length n, and the doubling constant will be just under 2. And we will say that if we think of a as being very large and c as being some fixed constant like 15 or something, then if we get that a plus a is less than or equal to c times a, then we'll say that a has small doubling. But of course, that's not completely precise because the word small is not totally precise. Nevertheless, it's precise enough to ask a question which you see below to an LLM. Must the intersection of two sets with small doubling of the same size have small doubling? Now, I've just put up there an example to show that you can have sets that don't have small doubling at all. So if you take a set of powers of 2, then no two sums are the same except in trivial circumstances like 2 plus 8 equals 8 plus 2. But apart from those, you don't have any coincidences, and so you get a doubling constant of n plus 1 over 2, which tends to infinity with n. So this set, we would say, does not have small doubling, and that's actually that's the worst you can do. So how might we go about solving the problem? Well, one thing we do when we're solving problems is look at just slightly different questions provoked by observations that we make. So here we might observe that A intersect B is a subset of A. So we could ask an even stronger question. Instead of just asking, is the intersection of A and B a set of small doubling, is it always true that if you take a subset of a set with small doubling, then you have a set with small doubling? And I hope you can see that the answer to that is obviously no. You just take, well, the example we end up with is you just take a large arithmetic progression, and inside it you can find a set of, so we can find a set that's got very large doubling. So we could all think of it the other way around. That's what I've written here. You could take a set with very large doubling, like the first n powers of 2, and just include it inside an arithmetic progression that's sufficiently long to contain it, and then you have a very obvious counterexample. Once you've done that, we say, okay, that failed. Perhaps we can learn from that and get a counterexample to the main problem. So what would we do there? We'd want to find a set So we want to take our example for perhaps that we just had, so of a subset of a set with small doubling that has large doubling. So the set with small doubling is all the numbers from 1 to 2 to the n minus 1. The set with large doubling is the powers of 2 from 1 to 2 to the n minus 1. And if we could make that set the intersection of A and B, then we'd be in great shape. But B has to satisfy certain conditions. Like B has to be the union of this set 1 up of the first n powers of 2 with some other set which needs to be disjoint from A. And we also need that the set that we've constructed like that should have small doubling. So the next thing we could do is just forget about the condition of needing it to have small doubling and just say what's the simplest set that we could add on to B, or sort of add on to 1, 2, 4, 8 up to 2 to the n minus 1 that would be disjoint from A. And we could just take the next 2 to the n minus n integers, 2 to the n minus n, so that B will end up having size n. So that's the most obvious thing to do. And then we could just say, well, perhaps that works. Well, we can check that by seeing whether it really is the case that B defined that way has small doubling. And don't worry too much about this slide. It's very easy to check that the set that we end up with like that does have small doubling. And in that way, we have a counterexample. That was a fairly easy problem, but I just wanted to spell out a kind of way, the human, if you saw that written down in a textbook, and this is one of the main points I want to make, you might see the small doubling property is not inherited under intersections. For example, consider the set A equals this and B equals that, and we check that it works. And if you see it written down like that, you don't see any kind of process of arriving at this set B. You just, well, in particular B, but also A and B. You don't see how the example was constructed at all. Or, sorry, you see how the example was constructed, but you don't see how the example was thought of at all. You just see the example and you see that it works. So let's just now see what happened when I gave this problem to ChatGPT 4.0. And I can't go through the whole thing because then we'd be here all day. It was a very long and annoying conversation, as it often is when LLMs don't manage to solve a problem. But it gave some not completely ridiculous initial thoughts. So it had the idea of making A be a long arithmetic progression. The slightly shifted version of A had nothing to do with anything, really. I don't know what that was all about. I'm not quite sure what shifting B more randomly means. But then it sort of seems to change its mind and says that A and B should be completely different structured sets, which by structured set, I think it means something like an arithmetic progression. This is guaranteed not to work because the intersection of two arithmetic progressions will, in fact, always be a set of small doubling. But it does at least say, it does notice that small subsets of sets with of structured sets can still have large doubling, particularly if they're random. Random just means sort of structureless, and I think for this purpose, the set 1, 2, 4, 8 up to 2 to the n minus 1 would count as sort of random. So it has some sort of good ideas. I'm not sure it really recognizes whether they're good ideas or not. So there's not really evidence that it's. I think this sort of fits more like the stochastic parrot interpretation, that it's just writing things that are the kinds of things that it's observed additive combinatorialists writing when faced with questions a bit like this. But that means that some of what it writes does make some sense. Then it just proceeded to give me various examples that don't work. So, for example, the first suggestion was that A should be the set of the first, well, for everything from 0 to 99, be a random subset of A. But the trouble with this was that, first of all, A and B don't have the same size, but that's a minor issue. More important is that because B has density a half in A, this B will have small doubling. It's just too big to have large doubling. And maybe I want to make sure I don't run out of time, but the second example here actually is getting a bit closer. So a seed-on set is just a set that has a maximally large, has a doubling as large as possible. So this is actually looking quite similar to the example I presented, and it's something that could be made to work. You take A to be the union of C with a long arithmetic progression, and B the union of C with another long arithmetic progression. But it doesn't say anything about those two arithmetic progressions, and it's important, for example, that they should have um, the same or pretty similar common differences, and also that they should be longer, for example, than the difference between the minimum and the maximum of the seed on set and that type of thing, which it doesn't say. So you're not confident that it really understands what it's just said. And so I'll leave that there. Um, and just think about what where it was seems to go wrong. So I think one of the main problems is that when it gets stuck, what is a human? So first of all, there are two moments that are difficult for a human mathematician. One is we just get stuck completely. We just say, I have no idea what the next step of this argument is going to be. Um, and in that situation, the response of a human will tend to be, well, I don't see what to do next, so let me formulate another question that's related to the question I've got here that will ended up be easier but relevant to the question. So, for example, you might drop a hypothesis and find that you then have an easier problem to solve, but because you've dropped a hypothesis, the answer turns out to be a counterexample to the thing you were trying to prove, and with the hypothesis removed. But at least then that counterexample we can learn from and try to understand, because presumably the counterexample will fail the hypothesis, but you can then try to get some insight into why the hypothesis is relevant. And you do things like just one of the things we've been thinking about quite a lot. Um, I and people in a group that I have is how you actually learn from counterexamples. And one of the answers to that is that we try to generalize them as much as possible so that we can get properties that any counterexample would have to have, which you can then, with any luck, use to get a contradiction to the statement that there exists a counterexample. Somehow an LLM, when it, but yeah, going back to when you're completely stuck. So we as humans will tend to formulate different questions. LLMs tend just to sort of make a guess, find that the guess doesn't work, make another guess, find that that guess doesn't work, make another guess, find that that guess doesn't work, and so on. So I call that guess and check. I call that method. You make a guess, you check whether it works. If it doesn't work, you make another guess, and so on. Or maybe you could call it trial and error. Um, but a human will, first of all, there's this process I just mentioned of formulating other questions. But a second thing that humans do very much more than LLMs, in my observation, is that if you make a guess and it fails, you don't just sort of say, oh, that didn't work, let's try another guess. You say, well, why did it fail? I've just been sort of discussing it. Why did the guess fail? Any guess that has these properties must fail. So my next guess should avoid those properties, and you have a better guess second time round. You find a guess that avoids the properties that made the first one fail, and then you sort of iterate that process. It's not always easy, of course, but we have sometimes when you want to try and iterate it, you'll get a further problem that you get stuck on, and then you have to sort of do something recursive to get this process to work. And I'm not claiming that LLMs never do anything like that. They never adjust their initial guess, but they seem much more ready than humans are to abandon their guess completely and just make another wild guess. And I think the harder it gets, the harder the problem gets, the more they behave in this way. So I think this is the sort of failure mode, even if sometimes, and I get this particularly looking at the thought traces from Gemini 2.5, which I find quite interesting. I'm not saying that they never ever do anything like what a human does, but they just don't do it as much. And well related to this. If we want to construct something that's got two properties that look hard to combine, then an example of something we might do, instead of immediately trying to guess something that will work, we might instead create a class of examples that satisfy the first property. And if we're really lucky, that class will be parameterized, and that will reduce the problem to picking a value of the parameter that will result in an object that satisfies the second property as well. And that's a technique that can be very, very useful when you're looking for um, objects that satisfy more than one property at once. Even when you're solving simultaneous equations, you can do it that way. You can say the general solution to the second equation is blah, blah, blah. Now let's substitute that into the first equation and so on. So it's a kind of generalization of solving simultaneous equations, this technique. Um, so why is it that LLMs fail in this way, if I'm right in suggesting that that's what they do? I find that a principle that is useful for thinking about this question is just because they work statistically, um, if they're faced with two bits of text, and it's difficult for a human being looking at those two bits of text to tell whether they've got some property or not got that property, then the chances are that it's not going to be that easy for an LLM to distinguish. Perhaps there are counterexamples to this, but just as a sort of initial way of organizing my thoughts, I find it just a useful way of doing it. And so let me give some examples of what I mean by that. Um, so supposing we had an argument in the middle of which it said, since 3,435 times 2,681 equals 9208235, and then continued with the argument. If you read that in a maths book, you'd sort of look at it and see, oh, well, it's just over 3,000 times just under 3,000, and then the answer just over 9 million. That looks pretty plausible. It ends in a 5 as it should, so probably that's correct. But if we saw the second one with 9209235 instead, we would argue in exactly the same way that that looks correct. We would trust the author because we have no reason to believe that the author wanted to lie to us. And so we wouldn't be able to distinguish between those two. We wouldn't sort of, one of them wouldn't jump out as being correct and the other one as incorrect. Just in case you want to know, it's the second one that's correct and the first one is incorrect. And a similar thing applies to proofs. If you're not really reading a proof carefully and thinking about it and understanding what it's doing and so on, then you can read something that is a correct proof, and you can read something else that's just complete nonsense. And if it's reasonably plausible nonsense, you won't notice. It'll take a lot of work to be able to tell which one is the correct one and which one is nonsensical. So again, that means that, or at least this is how I see it, that an LLM, the fact that LLMs hallucinate is sort of understandable because they're producing things that they don't particularly see the difference, arguments, they don't really see the difference between what they've written down and what a correct argument would look like. This doesn't completely explain how they sort of blatantly contradict themselves and things like that, but I think it goes some way towards an explanation. Then this is just a third thing here is a subset or subcase of what of the second case, that in particular, if you're asked to find an example of an object with a certain property, then just seeing a correct example and a correct proof is difficult to distinguish unless you think about it quite hard from an incorrect example with a completely incorrect verification. And also something that's particularly important, I think, is that often in a maths textbook, as I've already said, somebody will just give you the example of something that has the properties and give you the check that it works. And if you're reading that, you don't know whether that's something that any expert would immediately have thought of, or whether somebody had spent several months coming up with that example that happened to be reasonably easy to check once they'd found it. Unless, of course, the author actually tells you, oh, this was hard to find, or maybe give some explanation. But often people don't do that. They just say this works and checks that it works, which I think is a big problem for training LLMs. Right. So here's just to illustrate that. The first sentence here, we can take p around log k and epsilon to be omega of 1 such that that equation holds, comes from a paper that's on archive. And then one of 1 and 2 is how the paper continues, and the other one is just a complete piece of nonsense. And so if you look at that, I'm hoping that you won't find it particularly easy to guess whether the paper continued with 1 or continued with 2. And unless you're really very expert in additive combinatorics, and the answer is in this case it continued with 1, and 2 I just invented and was complete nonsense. And I think an LLM would just, again, not really be able to. The fact that we find that hard to tell me is that it wouldn't jump out to an LLM as being nonsense. Okay. So I've already mentioned that when LLMs get, I've mentioned this second hypothesis. I just wanted to mention also an analogy with NP completeness. So, as we all know, the problem of finding proofs in general is an NP complete problem, or finding proofs of length n, let's say. If you want to find proofs, that's halting complete. But if you want to find proofs of length n, that's NP complete. But somehow we managed to find really quite long and complicated proofs in a time that seems quite reasonable. So something interesting is going on. We have ways of doing it. And I would hypothesize that the reason is it's a bit like the difference between supposing we had a quadratic equation like x squared minus 5x plus 5 equals 0, and we happened already to know that solutions to quadratic equations tend to look like integer, if they've got integer coefficients, look like integer plus square root of an integer divided by another integer. We wouldn't then say, let's try various possibilities for small integers a, b, and c until we eventually get one that we can substitute for x and get 0. Instead, of course, we would complete the square and work it out that way, or possibly just use the formula. But I think a better analogy is completing the square. So we'd have techniques for rearranging the equation until the solution became obvious. And I think something similar with proofs, and in particular, the part of a proof where you want to build some non-obvious object. I think we very often, well, one of the techniques we very often use is you turn that object into a meta variable. That is, we just give it a name. We don't choose it at all, and then we just try to simplify the conditions on that object until we do get something, a problem that's where the solution is obvious. So LLMs again do that a bit, but not nearly as much as humans do. So they use this guess and check approach too much. And I think it's because a lot of the mathematical literature is written as though guess and check was what was being done, when in fact it's not. So here's another example then. I asked for, initially actually, I asked for a subset of the reals that's dense but contains no 3 points in a line. But it turned out that ChatGPT knew how to solve that. So how you solve that is you just pick points one by one, making sure that you enumerate all the open balls with rational radii and rational centers. You want to make sure you get a point in each one, and that you can do by just picking the points one by one and just making sure with each new point that you don't accidentally put it on a line that that goes through two of the points you've put so far, which is easy because there's only finitely many lines so far. Anyway, ChatGPT knew that technique, so I then tried to make the problem more difficult by asking for an explicit example. So I wanted to define a property such that the set of points that satisfy that property would be dense and contain no 3 points in a line. So then you can't just pick points one by one, because then if you do that, you can't really describe what the set looks like. And well, let me just, I think what it did is good evidence again that it was using guess and check all the time. So the first example, it just wrote down the following property. And if you look at that, you'll see that if you don't think about the proof that it works for a moment, which is wrong, just look at the example. You can see that the example is contained in the curve y equals root 2x squared plus pi x plus e. So if it's contained in a curve, it obviously isn't dense. It's correct that it doesn't contain 3 points in a line, so it probably sort of used the fact that it knew that the graph of a quadratic doesn't contain 3 points in a line, somehow just didn't bother about the density. It claims that it's dense, but it's total nonsense. I maybe won't trouble you with reading through this nonsense proof. Let's have a look at the second example it gave. This time it gives an example that's dense. I complained about the first one, obviously. So this time it gives one that's dense. What it does is it, for each rational radius, it picks a dense subset of points of the circle with that radius by taking an irrational number and going around that multiple of pi, filling up. So it sort of knew from what it's been told that if you do that, you'll get a dense set. And it sort of had this kind of hunch that because it had chosen an irrational number, then that should make it possible to prove that no 3 points are in a line. But that's ridiculous because this is sort of radially symmetric. If you multiply a point by a rational in this set, you'll get another point in the set. So it contains lines with copies of the rationals. So it's completely not true that it doesn't contain a line with 3 points. It contains lines with infinitely many points. And then all this stuff about you can make this precise using results from ergodic theory is just slightly embarrassing because it's it's a false statement. So another guess and check. Then another third example, it tries doing something using the Cantor set. And again, it's just sort of looking at things it knows, thinking, oh, this looks like the kind of funny problem where a Cantor set might be useful. And this one is worse, actually. It's not dense and it contains lots of lines with more than 3 points in them. So that's an absolutely hopeless attempt. Um, and oh, so this was the proof that that third example doesn't contain 3 points in a line. I like the phrase, this is the deep part, but I think I will just jump on because, again, I don't want to, it's not, as I said before, the purpose of this is not to laugh at LLMs, it's just to try to understand in what way they go wrong. Uh, let's go to Gemini 2.5, which is often better than ChatGPT in my experience. So it too started off with an example that fits inside a curve, but the words this construction doesn't work and so on are Gemini 2.5's words, not my words. So it noticed straight away, having made this guess, that it didn't work. Sorry, those are my words. But anyway, Gemini 2.5 in its thought trace did recognize that it doesn't work. Oh no, wait a minute. Sorry, that is not that doesn't live in a curve. It doesn't work because if you fix x, then you'll see that you can choose lots of different y's for that x, and so therefore each vertical line contains a translative q. In fact, it contains it contains a translative q. So it contains lines with lots and lots of rationals in them. Um, but it's not a bad example. I'm guessing that it had seen something like this somewhere and didn't actually come up with the idea for itself. Um, and it actually gave a correct proof. It's not that hard actually to prove that this example doesn't contain any 3 points in a non-vertical line. So then it, having seen that that doesn't work, I said I really do care about vertical lines. So it gave some other examples. This one lives inside a curve, which the next one, which it noticed. The next one, just, it's the kind of thing that you might see for this kind of problem, but it completely doesn't work for this example because for almost all x and y, x, y, and 1 are linearly independent over q, and so therefore you're definitely going to be able to find lots of lines with lots of points in them. Um, and Then, yeah, another example. This one doesn't work because you can multiply every point by a rational and it'll still be in the set, and so on. So it goes on producing wrong examples, guessing and and checking and sometimes thinking it had an example, sometimes noticing that it didn't. But what was it not doing? So it didn't do this process of successive adjustment of an example. So a human faced with the first example that Gemini 2.5 had given, that once discovering that it didn't work, wouldn't just immediately give up and say, okay, that didn't work. We would say, we actually dealt with almost all lines there. It was just the vertical ones that were a problem. And a natural thing to wonder at that point is whether we could just deal with the vertical lines by picking at most 2 points from each vertical line, um, and in such a way that the set remains dense. And if you start thinking about that, you can see very quickly that that's quite an easy thing to do. And it's not that hard. I'm not going to give the details now. It's not that hard to proceed with that process and actually get an explicit way of choosing from each vertical line in that set, an explicit way of choosing 2 points, so that you will end up with a dense set. So that's a technique that I would call guess and adjust. So instead of guess and check and then re-guess when the check fails, you guess and check. If the check fails, you try to generalize the reason for the failure as much as you can, and then adjust the example to avoid that reason for failure. And again, I'll just say, as I said before, it's not the case that LLMs never ever adjust their initial guess rather than abandoning it, but they don't tend to adjust it. I mean, they tend to be sort of, again, too quick to give up on that process. And they don't seem really to sort of analyze um, as much as possible the reasons for things failing. Um, so let's now think about what we could possibly do to make things better. So this picture, um, I should say, is something that I couldn't find online, a freely available photograph of a rabbit out of a hat, and still less a rabbit out of a hat that's crossed out. So this picture is meant to convey that we don't want to give LLMs training data that involve lots of instances where we just pull a rabbit out of a hat. We say, here's a construction that works, and here's the verification that the construction works. So to get this image, I feel credit where it's due. I just found some random site online, say, by Googling free AI generated images or something like that, and I described what I wanted, and that's what I got. So I feel as though the last few days my use of AI has suddenly increased, and I think I may have sort of reached a slight sort of tipping point there. So we don't want that. So what can we do instead? What we would want to do is present a lot of data, training data that actually presents in a careful way how we come up with these examples. So they're not rabbits out of hats at all. There's no magic. We have processes for finding them. Um, and of course, the notion of chains of thought is a very well-known one in training LLMs. And I think my contention would be that the chains of thought that we have at the moment, and here's something where I may be out of date, but anyway, or I may just not know about everything there is to know about. But my impression is that the current chains of thought are not quite what is called for. So a lot of them will be just working through things like solving simultaneous equations or um, applying rather standard techniques in a rather standard sort of way. And of course, that's useful and maybe helps to stop hallucinated answers to calculations and things. But what I'm interested in is finding these non-obvious steps in proofs, and in particular, constructing non-obvious objects to have various properties. And there are some more sophisticated chains of thought around. I'll give an example in just a moment. But I feel uh, they're still not really um, conveying how I myself and other mathematicians actually go about solving problems, particularly when the problems get quite hard. So here's an example of one from the LEMO database, I've now forgotten what that stands for. Less is more or something like that. But I won't even say what the problem is. I just want to show the style of the chain of thought here. So it's full of words like wait and okay and let me think about this and so on. And I feel that that's not the. And I think I heard that these chains of thought were actually generated by LLMs themselves, which in the end I think is unlikely to. It may get. It seems that experimentally these chains of thought were helpful, but I think they're not going to get us too far um, because they're not really sort of giving a kind of general method. It's not as though they're explaining a general method for how to solve problems. And maybe I can give a couple of, can zero in on one or two things that I find inadequate about this. So here it says, I remember that when dealing with co-prime numbers, their prime factorizations don't overlap. So it seems there that it just uh, had the idea and then didn't really say where the idea came from and just said, I remember that. And there's an even better example of that a little bit later on in the same chain of thought in this problem. Um, so it says, so maybe, uh, so did somebody say something? Yeah. Maybe this is a problem related to the number of ways of factoring 20 factorial into two co-prime factors. What the question was, I think it was asking for something like the number of fractions in their lowest terms where the product of the numerator and denominator is 20 factorial. So in fact, this first question is, and they had to be between 0 and 1. So you want the numerator to be smaller than the denominator. And so it is indeed exactly the number of ways of factorizing 20 factorial into two such factors. Uh, and then to the question, how do we count them? It just jumps straight to the answer and puts, I remember that. So it's not really giving a chain of thought that would be helpful to another LLM. It would be saying to that other LLM, if you don't remember how to do it, then that's just too bad. Uh, and again, let me recall, blah, 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 would be 2 to the k minus 1. Um, so, and I've looked at other chains of thought in that database, and they all seem, again, not to be sort of totally helpful for these sorts of reasons. So what could we do instead? Well, I want to talk a little bit about, and I'll finish very soon, but just a little bit about some plans that my group in Cambridge. And by the way, I'm very happy to see that a lot of the speakers today are people who've interacted a lot with this group. So what we would like to do is produce what I think are semi-formal chains of thought. So by that I mean actually come up with a kind of rather systematic way of presenting mathematical chains of thought, identifying moves that one does, like generalizing something or specializing, looking at a special case, taking a counterexample, generalizing the proof that it's a counterexample, which raises another issue, which is how do you generalize proofs, which is something else that we've worked on, which I haven't listed here, but in which some members of the group, in particular, Anand Tadipatri and Anshula Gandhi, have made a lot of progress on. So what we want to do is identify these moves, and we've got a big collection now, but when I say largely done, that's because I don't think it's a complete set of moves, but it is a set of moves that is already capable of being used to generate quite a few non-obvious proofs. Because each move is a reasonably well-defined thing, it should be fairly easy to train an LLM actually to implement them. And I've experimented with explaining to ChatGPT, this is what the move is. Here's a sentence. Can you apply, or a mathematical sort of proof state? Can you apply the move to that proof state? And it does pretty well. So I think that's not going to be problematic. So the next step would be to create a website that, because writing down by hand, one of these semi-formal chains of thought is very laborious. And if we want to create a database, we don't want entering each entry to be very laborious. So the idea would be to create a website that will do quite a lot of the process automatically. So users would just say, I want to do this generalization move here. And then an LLM would say, does this look okay? And then you'd say, yes, that looks okay. And it would, and so on and so forth. Um, we would also like to be able to do the same, so that would all be in natural language, but we'd also like to be able to do the same thing in a more formal way using lean, developing lean tactics. That has the complication that what we think was a proof discovery state is rather more complicated than a lean proof state because we're considering all these subsidiary questions which have various logical relations between them and so on. But various people in the group have made quite a lot of progress on that. I just mentioned in particular, as well as Anand Tadipatri, Jovan Gerbscheit and Mirek Olsak has also contributed to that. Um, so that's in progress. And we would like to create an interface that would enable that to be done in a convenient way. That's started a little bit, but that's a lot to do there. So once we've got these tools to make entering semi-formal chains of thought convenient, then we would like to produce a large set of examples so that we've got a database of maybe sort of 1,000 proofs together with these proper chains of thought that could then be used to train and I hope improve the performance of LLMs and mathematics. It's a bit of a guess that that will actually work, but I'm fairly optimistic about it. And there are also other things we can imagine doing. I'm talking about LLMs because that was a theme of the workshop today. But I can also imagine if you've got these sequences of moves, particularly if they're implemented as tactics in Lean to use to train a reinforcement learning. And I've been discussing that with various people in Paris, such as Fabian and Maury, and we hope perhaps to do something along those lines as well. Um, I was just thinking as I was preparing this talk, it would be quite nice to have a benchmark of the kinds of problems that it would be nice to be able to solve. In particular, these sort of creating non-obvious objects. Since I'm running out of time, I think I will just. There was a potential example, but I think I'll just jump to my conclusion at this point. Um, and so these are really things I've already said. That I think the current LLMs use guess and check too much. Often their guesses are good, which means they perform pretty well. But I think that there's a sort of plateau unless we can somehow convince them not to use guess and check so much. In order to convince them of that, we need to give them data that doesn't pretend that guess and check is what is being used to find proofs. Um, the current chain of thought goes some way towards that, but I think we could go a lot further, and that's what we're hoping to do in the reasonably near future. So thank you very much.
Question, so we'll have to see if the microphone works. But, any questions?
I actually have one on the mathematical constructions you were talking about. So the goal will be to have mathematical constructions that wouldn't be too hard for a human, but that an LLM couldn't do. Do you think there is a chance that the new state-of-the-art LLM that can also use tools, external tools, could be able to essentially bypass the difficulty in this direction? That could be something we could view. I mean, make sure it won't do.
Which external tools are you talking about here? So the difficulty I'm talking about is difficulties of finding proofs.
Yes, of course. But sorry, I thought the difficulty was to find the mathematical construction. But then once you have the construction, proving that it actually works is easier. But actually, that's not right. The difficulty is even if you have the mathematical construction, finding the proof will be hard. Is that all right?
Well, if you're talking about the sort of benchmark suggestion that I made briefly towards the end, I think an initial benchmark might be problems where the real difficulty is finding the object, but once you've found the object, it's reasonably straightforward to verify that it has the right property. Of course, that would be just sort of there exists. That would be a kind of a problem that's quotes in NP unquotes. You can then imagine more complicated things where in order to prove that it has a property, it's not very easy. So that might be something that you could think of as being in an analog of pi1 or something like that, or I mean pi2 or Uh, and then there might be something where, in order to prove it, you find yourself needing to prove that everything has another sort of for all there exists statement. So the number of quantifiers increases and you get a sort of nested difficulty, or sort of going up the polynomial hierarchy. But I was imagining problems um, of the first kind because I think once you can do those well, it should make it easy to do the more complicated ones. But I don't know whether I'm completely answering your question there. Um,
I think so.
I have a question. Can you hear me?
yes.
Yeah, so I mean, it's a very interesting talk. You've obviously spent some time looking at these reasoning traces and gained some insights into their abilities and failings. Now, a related, but to my mind, a little simpler hypothesis about problems like the hallucination, like not sticking with an idea and trying to fix it, but abandoning it and guessing again is to say that to ask. First of all, does it represent these things? So like if a statement proven is a statement of hypothesis, it's a statement of hypothesis that we should try and perhaps abandon, is a statement important so that we should continue trying to modify and improve it. And so one could ask, well, how can it represent those things? And as language models are now, they generally represent them in the text. In the reasoning case, they explicitly say, yes, this is an important statement, or this or not. Yes, this is a proven statement. Let's not keep trying to reconsider that. And so my general question would be, to what extent do the reasoning traces contain those types of tags, as opposed to or not?
Let me just say, if I understand you correctly, what you're saying, which sounds very interesting, is that another sort of, and it's not clear which is more important, but another sort of problem is that maybe something one might think of as lack of short-term memory. It would be sort of not thinking this
Right,
is.
exactly. Not representing things which for us are sort of automatic features of short-term memory. We don't know how they work, but it's only short-term memory as its window. It's text context, and so it would need to explicitly represent these things. And one could, of course, encourage that through the training.
Right. It's sort of another manifestation of the sort of general idea that they're not in some level, at some level, they're not really thinking because they're not.
We're not thinking well,
Yeah,
again.
maybe that's a better way of putting it because obviously they are. Yeah, I don't want to. I don't, but that's what I meant to. Yeah.
The same general strategy of let's find the missing points and now supplement, you augment the training data to really boost those missing points.
Right. Right. Um, yeah, maybe that's something to bear in mind. Actually, that yes, that um, there should be some way of encouraging it to sort of maintain its list of things that it's concentrating on, perhaps suitably represented or something, or even if it's just, as you say, I think I heard you say, just giving a tag to various things and saying, here are my tagged statements that I'm keeping at the forefront of my current
Right,
ambitions or whatever.
right.
Yeah, so I don't, not having thought very hard about that particular point, I don't have an immediate view about the relative importance of that as against what I was suggesting.
That's very valuable.
But I'll think about that. Yeah.